Right. Thank you, Ewan, and thank you for the organizing for the opportunity to speak in this wonderful location. So today I'm going to talk about an approach to use homology theory to study links and knots. So for me, a link is a nice embedding of a bunch of structures to the tree sphere. And the approach we're going to take is inspired by what's called the category 5 link invariants, or sometimes also link homologies. And how these things usually appear is you start with a combinatorial description of your knot. This is a two-dimensional picture of a knot represented as an closure of the break. The combinatorials here will be that of a breakboard. And then using that information, you can cook up a chain complex using appropriate algebraic structures, maybe a double or triple chain complex. Then if you're lucky enough, when you take the appropriate homologies, then you get something that's actually an invariant of the link and doesn't really depend on the presentation you chose for it. And the algebraic topology I'm going to talk about today happens roughly at this stage. So we're going to look at this kind of complexes and homologies that are originally defined algebraically, and by interpreting them in terms of perhaps equivariant homology of adequate spaces, then we can obtain additional structure perhaps, or explain some of the already present structure in these things, and then defining further invariants this way. So the algebra today is going to be that of certain bimodules over a polynomial ring. These are like very classical objects in representation theory. And then let me start by defining the most basic building block. So we have a polynomial ring in two variables, x1, x2. I'm also going to look at the subring of variable polynomials, which are invariant on the permutation of the variables. It's defined by the two elementary symmetric polynomials. It's generated by that. And then the elementary Bott-Samuelson bimodule is what I get by tensoring R with itself over the invariant polynomials. You can also look at this as I have four variables, x1, x2, y1, which are like left and right variables, and then any symmetric expression with the x's I identified in the same symmetric expression in the box. This is nice bimodule. Is not this as a module of the R is not too terribly complicated, but then I want to redefine this thing using equivariant homology. So, and we're going to keep running this parallel story. Then, in this situation, I want to look at a torus in a unitary group. So these are like diagonal matrices in the unitary group. Of rank 2, and the polynomial ring appears as the cohomology of the classifying space of the torus before the equivariant homology of the point. And then I can mod out the right action of the torus on U2. This is something that's usually called a flat manifolds, but in this small case, this is actually just a sphere. Now, I modeled out the right action by multiplication of t, but there is still a left action. I can multiply by elements of t on the left. So then there's still t space, where t is the torus. And it turns out that the elementary Bott-Samuelson bimodule is also the equivariant homology of this thing. So you might be wondering, how is this bimodule? But I mean, this is equivariant homology of something. It's typically a module over the coefficients, but I'm claiming that it's a bimodule. So I'm going to explain this because in the way I'm going to introduce a little bit of the underlying geometry that's going to be useful later in the talk. So by definition, equivariant homology is built in this way. I take my space E through mod T, and I take product with a contractible ET that's like large enough to accumulate free action of T. This is what's called the Borel construction. And then when I write x sub t, that's quotienting out the diagonal action. So I can basically freely move acting torus elements from one factor to the other. That's the relation. there. In this particular situation of torus and a unitary group, I can take this space ET to be frames in infinite dimensional complex space. So the pairs of orthonormal vectors, you have a torus action on this thing. Turns out to be contractible for ET. Then your classifying space is obtained by modeling out the T action. So what happens is there are like two very naturally defined maps from this so-called world construction into the classifying space. You have a frame and a matrix which represent an element here, then I can either just remember the frame to represent an element of the classifying space, or rotate the frame by the matrix, because secretly I can also act in frame by element of U2, and then that new frame represents something in B. So these two maps induce the two actions that give me a bimodal structure on that map. And actually, briefly justifying why this is the same thing, this map actually fit into a pullback diagram like this, some standard arguments in spectral sequences allow you to conclude that the cohomology of the pullback can be expressed in terms of the cohomologies of the other things, which ends up giving you the original algebraic expression you get the bimatrix. So this is kind of like the most, like the smallest space underlying the smallest bimodule that we're gonna work with today. And then in general, we're gonna work then with n variables. We can look at invariance under the permutation of two consecutive variables. This is the subring of R. And then we can define what are called the plot bounds. So if I have a list of indices for I from 1 to n minus 1, that's how many prime positions you're allowed to have of this kind. Then you can assign the kind of like the base ring to the empty sequence. You can assign an elementary bimodule to a one in the sequence in the same way that we define the case n equals to 1. And then for an arbitrarily long sequence, I1 dot ik, I can tensor these things together, and they still are bimodule by the left and right action R. So we can define, like, put all these things together into a category. So far I've been referring to both samples and bimodule, which I just showed you how to define in general. But from the original representation theoretical perspective, it's interesting to consider the whole category closed under these operations listed here. So I'm looking at all the bimodules over the polynomial ring and variables that are generated by these guys I just showed you under the operations of gradient shifts, direct sums, and crucially direct sums. Some like interesting indecomposable modules show up when you take direct comments, but those won't really play much of a role in the function. That's the category of Soergel bimodules. The morphisms are just bimodule. This is a full subcategory. Here is a couple of algebraically defined ones. I'm not going to talk too much about this. We're going to use them a lot. No, I'm not going to talk too much about this. They have their formula as well. But what I'm going to do is actually show you what they are on the equivariant cohomology side of things. So now that we're looking at rank n, we have a slightly more room in our topological description. We're going to be looking at, again, a maximal torus of diagonal matrices in the unitary group. And there are these intermediate groups of GI, which are like slightly larger than a torus. So the torus are like diagonal matrices. GI is almost diagonal matrices, except that you have a 2x2 block that sums up, right? So you have n-1 such things. You can again define an elementary plot Hamilton space by modeling GI by the P action, and it still happens again. The coefficients are the polynomial ring. The equivariant cohomology is the elementary bimodule. And then these two elementary maps are induced by a very canonical thing, which is inclusion of the base point, right? There is like a natural base point here in GI mod T, which you can think of as maybe the class of the identity matrix. And the inclusion of that induces these two maps. So I pull back, this is in cohomology. There is also a wrong way map. And if you see there is a shift here by two, ultimately what's happening here is that a representation sphere, such as those that appeared in the last talk, is behind this wrong way map. But it's still a logically defined map that comes induced from the inclusion of the base point. And then now I'm going to tell you how we use these things to talk about braid stability. So this is a braid group, a very well-known group. You can think of n strands as generated by twisting two consecutive strands, or the inverse of that generator is twisting the other way. You have group relations. And then Raphael Rouquier considered the following construction. So what you're going to do is you're going to get complexes of bimodules generated by these two very small complexes, which are basically the two maps that I already showed you. So this first complex up here only has as a differential I over star, and then everything is 0. The underline indicates the 0 degree of this chain complex. Then the inverse gets associated with I over star map. And then for a longer braid word, you can tensor these things together using like in the sense of a tensor of chain complexes. And what you get is something like what I would call a cubical complex. So cubical in what sense? So if you look at it, each generator provides like R, which is the unit of this tensor product, and a BI. So what you end up getting is one dot Samuelson bimodule for each possible subword of the longer word element. So I mean, the coming across here is like that of the cube of all the possible, the cube of all the possible subwords of that. And then the differential of this thing is ultimately again even induced by a bunch of maps that will come from nice inclusions of equivariant banks. So Rouquier proves that this complex doesn't really depend on the braid word, it only depends on the actual braid. So if two words are equivalent by braid relations, then you get homogeneity equivalent complexes of bimodules. And you might be wondering, like, okay, if this equivalence is like how coherent can I make them? So this is something that has inspired like a lot of work recently, and there's this recent result by a few authors here that looked at Rouquier's work and the nice properties that he's like explicit identity find. And then this is like a fully coherent picture. So long paper hasn't made much about it, but basically you can build two categories where like your objects are natural numbers, your morphism spaces are these spaces of complexes, and then your coherent like braid group action ends up being coded in this E2 model or like braided model structure. But as I said in the beginning, what I want to do instead is use the Soergel bimodules to talk about links. So we already have braids, and you can get links by closing them, by joining the opposite end of a braid. If you want to get a link variant, you better satisfy this Markov moves. So Markov moves just tell that if I stack two braids and close them into length, and then I take one of those braids and slide it all around the closing strands, that should be representing the same length. This is what's called a Markov move. So if you want invariance of lanes, you need to satisfy trace conditions like this. So an invariant that doesn't care about whether you write B12 or B1. So what Kavanagh did was, well, look at these Mejia complexes and use partial home. This is like the derived trace. This is something that by design satisfies trace conditions. So we already mentioned our cubical Mejia complex. And what we're going to do is, well, take partial homology at each spot, right? At each spot, we have this nice of the samples by module, take partial homology of it. This should be invariant under Markov moves by design. And then you also have a differential, which is induced also by the conformality of the partial homology, right? So what happens is by doing so, you get a triply graded abelian group once you take homology. So the three gradings here would be, we already saw that the B's are the homologies of something, so you can think of this like intrinsic Soergel degree. Then you have the complex, the Mejia complex, and call that a cubical degree. But now there is a partial homology, there's a partial complex there. There's also a partial. So it's a lot of grading. It turns out that if you choose your grading conventions correctly, this is the link invariant. This is what it's called the Kavanagh-Borsansky triply graded length homology. So this is a rather large thing. So the unknot, which is our simplest knot, this is already infinitely generated over, right? So sometimes if you want like better finiteness properties, you're probably looking for link invariants that that don't really behave like this. All right, so what is the full topological picture? I already gave the full algebraic picture, right? You have a complex associated to the braid. We take partial homology at each spot. Then you can get link homologies by doing it. So just like we did for Butt sonnets on bimodules, we can also build corresponding Butt panels on spaces. The idea is similar. For the trivial indexing sequence, you get the torus, which is kind of like our base thing that's actually on everything else. Then you have BSI by noting how GI.T, we also saw that. And then for a longer indexing sequence, what you can do is you can take like iterated products of these groups. And as you would expect, the homology of this general things do indeed give you the bimodules with the corresponding indices. But what about the partial homology, right? Partial homology of Soergel bimodules. How can I see that topologically? And the answer is given by a slight variation on this Bott-Samuelson spaces. So if you look at this space, it's written almost identically to this BS here. This X here doesn't have a quotient in it. So you keep, you don't model the right force action on the end, and you instead consider a conjugation action that will be acting on one side with force on the left, and the other side, right, with the inverse of the force. This thing, of course, projects to both Hamilton by just modeling out the action on the end. And what's interesting here is that you can again fit everything into a pullback diagram. And this is the kind of situation that, again, by using the adequate spectral sequences, can let you can allow you to identify the algebraic situation. So in this case, what happens is, again, we have pullback diagram. The cohomology of the pullback gets identified with a derived transfer product of all the other things. So R tensor R, E, I1, okay, R, those are all the ingredients in the definition of partial homology, but those are also the cohomologies of all the other corners of my diagram. And there is like a collapse argument that tells you, yes, this guy is indeed giving me the partial homology of Soergel bimodules. So, right. So I have then identified all the terms in my Cavana cubical complex as equivariant homologies of some, right, of these X spaces. So can I use that to get additional structure here? One approach is map compatibly into a fixed space. So why would that help? So if this whole cube is built out of cohomologies of these things, the differential is built out of inclusions of these things, then but can map compatibly into a fixed space U respecting those inclusions, then what I get is a well-defined module structure up there. So you induce maps and cohomologies, and what you get is the partial homology of box Hamilton module, equivariant homology of X, half a module over whatever U is of its cohomology. So what we want to do is do such a construction in a nice controlled geometric way. I'm going to take point literal U to be the infinite unitary group, but as the column of the full defined ones. And you can think of its elements as unitary transformations in infinite dimensional complex space. Here is a nice map, it's like very geometric. So ET, we said that's a frame, it's infinity. Now it's an n frame because we're thinking of rank n. So we have n vectors infinity. And this x of I1 xk is just the product of a bunch of subgroups of UN. So each of these G1 gk, they're just unitary matrices of UN. So what I'm gonna do is like to cook up a transformation in C infinity. What I can do is, well, look at the basis given by the frame and its complement. Do the multiplication transformation in the frame subspace and do nothing in the complement. It's an absolutely defined map. And it's easy to check that it respects the inclusions that appear between all these xi spaces. And then what kind of structure this is giving me? Well, the cohomology of the infinite unitary group is serial algebra in a bunch of odd degree primitive generators. So these are odd degree classes, meaning that they square to zeros. So what happens is when you pull back any of this, you can think in some sense of this as like a characteristic class, except that it lives in odd degree. So it squares to zero. Multiplication by such classes then is a differential in the cohomology of the X spaces. So you can then define a first, well, let's say, version of a twisted cohomology here. You can define the E beta n twisted cohomology of a space over U as precisely the cohomology of Y, then you take homology with respect to this new differential beta n. So I kind of have like a new sort of, I'm not claiming that this satisfies any generalized cohomology theory, but again, this sort of family of cohomology theories that work any possible space over U in a functoid way with respect to maps over U. And then one result in the linked cohomology world is that when you use this twisted cohomology in the Kovanov complex, then you indeed get again a link invariant. but this one looks a little bit different. So this is the same cube as before, but instead of, so I'm just taking an additional cohomology with respect to this beta eigenclasses here. And then when you consider the total homology of the full plane, you get invariant planes, which has these values. So it's, for instance, it's something that's finitely generated. That's for the unknowns also generally the case. This is related to known invariants, so this can be called if you're interested, an integral version of covariant response as well. So for instance, for n equals 2, this is like an integral version of covariant homology. And then one might ask, well, okay, we can already obtain some other link invariants from the Soergel bimodule approach by using the topological structure. What additional topological structure is there to take advantage of? For instance, you can think of cohomology operations like Steenrod squares, right? Everything here was built out of the cohomology of something. Maybe you take like integral operations already worth mod to, and then you can ask, are my operations compatible with the differentials, or my operations compatible with the differentials that come from the cohomology of U? Can I get symmetries of my linked models by doing this, or maybe relations between linked homologies for different ends? That's something. But perhaps more interesting question is, how does the more abstract machinery of twisted cohomology theory apply in this situation? So there is this homotopy theoretical notion of twisted cohomology theory. The perhaps most prominent example is what's called twisted K theory. So twisted K theory is something that roughly you can define for spaces over an algebra plane KZ3. So for instance, in our particular case, we have a chosen class in the third cohomology of U, which we call beta 1. So it directly applies to our situation. And then these twisted equivariant homologies are like more refined versions of what we just did outright. So in this kind of situation, you can get stuff like this kind of spectral sequence. This is like what the Hirschberg spectral sequence for twisted K theory. And it basically starts from singular cohomology, which we kind of have already been studying, and converges to this twisted plane where P is the twisting class in H3, right? Then what the kind of things that appear in these spectral sequences are also the kind of things that we've been talking about. You get multiplication by your class, and you get singular cohomology. So this kind of formalism may allow you to get a perhaps answer link homologies, and more importantly, there is like a lot of conjecture saying that two link homologies should be related in a certain way that in many cases should amount to some sort of spectral sequence deal. So we believe that many of those spectral sequences have justifications of this kind. And I'm going to stop there. Thank you very much for your attention.
There's a way to turn them into something geometric. So since they're all relying on first of all, definitely will not move to the day, and then start to compute. Right. I think there's any, and since now there's so much technology that you can kind of open what's all of them in.
Yeah, so one relation actually has to do with the last thing I said here, that there are like spectral sequences between different theories. Some of the ones actually defined in a more inclusive geometric way. Like for instance, there is something called instant not cohomology. that considers like connections on the component of the knot. And then by, this is work of, Frankheimer and Rockwell. And they get this kind of spectral sequence where like, you take a situation like this, and if it's simplified enough and like projected to the plane, you get a spectral sequence relating this thing, let's say, cohomology or something like that. So there are already like connections between like linking variants defined in this kind of like combinatorial resolving way, and in the more geometrical way of like looking at the knot principally as an object embedded in S3. And we hope that that this algebraic topology techniques might elucidate some of that.
The equity is the pre-Donat direction, or I also have like
in this, so yeah, there are higher cohomology, so there are like massive products going up in P5 and so on. There is no claim. Like, I mean, it will be wonderful if maybe for the particular space that we're interested in, that happens. Or maybe it would be wonderful if it doesn't. It depends on what one the kind of structure you want to get. But abstractly, this is the first non-trivial differential there might be. Even in the non-twisted cases, like the that would be related like cohomology with like even that. Yeah.
Oh, one more question, that's again.